Right. Welcome all to this 8th lecture of Principles of Statistics. In the last lecture, we stated, at the end of it, we stated the asymptotic normality of maximum likelihood estimators. And today we're going to devote the whole lecture to proving this theorem rigorously and to also, make some remarks about its conditions, especially. Okay, so how do we go about this proof? Well, I gave you sort of an intuitive idea of what are the main the main reasoning that we want to follow, and this was in one dimension. Now we'll work on more general dimensions, and let me also say that this is theorem 4 because I don't think I numbered it. Okay, so then in theorem 4, let me first of all fix some notation. So let me write PR for this infinite product probability measure under the actual theta naught that is generating the data, and let me also write, E for the expectation under that theta naught, which is the parameter generating the data. I remind you. Okay, so then let me first of all claim something and sort of justify this claim. So, and it's just to say that, so just, okay, so let me state it. So it suffices to consider, or to prove the theorem, in or on events En such that the probability of these events goes to 1 as n goes to infinity. Yeah? And this sort of should be intuitive, right? Because we're proving something in distribution, and so if we have that, we have some sets of probability approaching 1 in which things happen, then probably the statement in distribution should follow as well. Yeah. Okay, so how do we formalize this properly? So indeed, if we have some random variables Zn, so for all random variables Zn, we get that if we're looking at the probability, say, of this Zn being less or equal to some Z, so this is some sort of convergence in distribution, right? And we look at the equivalent quantity, but only under these events En, then we can bound this absolute value by simply the probability of the complement of these Ens, and so therefore this goes to 0. Yeah, and this means that we can prove convergence in distribution also in these sets, and it will imply convergence in distribution in the whole space. Yeah. Okay. So having done this, then let's look at some sets En where we can prove our result, and which will give us some something convenient. Yeah? And it's the following. So by the assumption, so by B4, okay. And this is, I remind you, essentially that we have consistency. So this is just then saying that this converges under this PR to theta naught. Then what we get is that the probability of, maybe write it down here. So the probability of this guy being in K, and I remind you that this K, we defined it as a ball of probability, a ball of radius R. So this is just the same as saying that, this is away from theta naught at most by R. Okay, so it was that ball centered around theta naught. So this is going to go to, so this is going to go to 1, of course, by convergence in probability, because this is 1 minus, the norm being larger than R, and convergence in probability tells us that for every epsilon, and in this case epsilon equal to R, it will go to 0. Yeah, that sort of complement of this. Yeah. Okay, so then in fact this gives us directly some ENs. Yeah, and more than that, so there exist these ENs such that this PR of En converges to 1, and more importantly here, where, not more importantly, but just as important, where this guy belongs to this compact set. Okay, and that's sort of important. Yeah, we'll see. I mean, that's important. And that's important. Yeah. So okay, so we work on these. From now on. Yeah. And this is a bit silent. So I will essentially work on these without mentioning it again. Yeah. Okay, so what do we have in these? Well, let's maybe get a picture. Let's imagine that we have, so this is the whole parameter space. And so I remind you the picture that we had. So we have an open set, this U of theta naught. Yeah? This is from the assumptions, I mean. So check them again if you need to. And then we have this ball. Okay, this K. Okay, and that's where eventually our estimator will live in, yeah, probably with high probability. Okay, so right, so let's now talk about some properties. So remember that the idea in this theorem is to prove, well, to use Taylor's theorem. Yeah. So then let's talk about differentiability a bit, and yeah. And then, yeah, okay. So let's talk a bit about differentiability. So note the following. So this log of fx theta, so this guy is going to be continuous, right? And not only continuous, but actually C2, yeah? And this is on U by assumptions. So on U, and this is for all x in here. So U, of course, is for the, so I mean, I'm talking about C2 for the theta parameter. Yeah? And this is due to A1 and B1. Yeah. Okay. So B1 is essentially twice differentiability of the F. But remember, if you take the derivative of a log, then you're going to get something in the denominator. You're going to get the F in the denominator, and so you'll need that to be strictly positive. Yeah. So that's where A1 comes in. Okay. So then, given this, so we're going to get what we want, which is that the gradient of this ln. Okay, the normalized log likelihood at the MLE is going to be 0. Okay, so that's the first thing. So then this and the function that takes us from the function in theta of this ln is going to be continuously differentiable. Yeah? And this is okay, and this, of course, on the same. So on U, but more importantly, it's going to be so in the along the following segment. So along, if you like, T theta n hat plus 1 minus T theta naught okay, and t being in 0, 1. So now this guy, of course, this path is going to be contained. So remember that we said that we're going to work on sets in which, you know, this guy is going to be there with high probability, and so essentially we're looking at this line between those two things. Yeah? Okay. Yeah. So all of this is contained. So this guy is contained in capital K. Yeah. Okay. So, well, or it lives in there. Okay. So then what we can do is, you know, the gradient is a vector, and so what we can do is that for each entry of this vector, we regard it simply as a function, right? A real valued function, and then we can apply the mean value theorem to each of those. Okay, so then applying the mean value theorem, which is something we did already, sort of in the informal proof that we had last time. Mean value theorem to each coordinate, to each entry or each component of this guy. Okay, then we get that 0 equals this gradient at this guy, which is equal to, so this is now by the mean value theorem, ln at the theta naught plus some an bar theta n hat minus theta naught, where this an is a matrix, an bar is a matrix that is going to be, or whose entries are given by the following values, which is the following. So we get the partial with respect to theta I of the partial with respect to theta j of precisely the log, or in this case, the ln theta. And then the key here is that this is going to be evaluated as an intermediate value, but this intermediate value is going to depend on j, right? Because we said that we're doing this component-wise. So this is for some, for some theta hat j, which is going to be given to yet again by, you know, some intermediate value between these guys. Yeah. Okay, so tj as usual belonging to 0, 1. Okay, and what is clear as well is that this guy belongs to this capital K by the same reasoning as before. Okay, so let's work on, you know, because if we look at this line that I wrote here, you know, everything there is sort of easy to analyze, as in the first term here will be, you know, that's just a sample mean, and you know, this guy is exactly what we want to sort of solve for, and so really the you know, the work has to come in through this an, and so let's write this an now more cleanly. So an, let's work on it. So we can write it as follows. So this is 1 over n. Let me just say then, maybe. So then we can write this as the sum from k equal 1 to n of the second derivatives, right? Respect to theta I and theta j of the log of fxk now of at theta j bar. Okay, that's important. And now what we're going to do is to, it's not going to fit. So let's just write then the expectation. I remind you that this expectation is always under this theta naught. Okay, and so the expectation of the same quantity. Okay, maybe we can write x1 if you like. and theta j bar, and this is important. It's, you know, the expectation. This expectation is with, you know, is integrating out that x1, but not this guy. Yeah. So this is still random. Yeah. So I don't want to integrate over the randomness of that. Yeah. Okay, so that's one term. Then, of course, you know, to compensate for what we subtracted here, we want to add the same quantity. Okay, so we have this x1, and then this theta j bar. And let me now subtract the same quantity, but evaluated at theta naught, which is a bit easier to handle, right? Theta naught. So then this guy, the second guy that I just added, is not random because the theta naught, of course, is not random, and the expectation has taken care of the randomness of that x1, while the first is random. Yeah. Okay. And then you know what we're left with is this guy. Yeah. Just to compensate for the other term. Okay, and let me maybe write, so the first, you know, the first line, I'm going to call it I, and then the second line, so the difference of the expectations is this 2, and then now we realize this guy actually is just minus the information matrix, Fisher information matrix at theta naught. Okay, so really what we need to work on is this first and second terms. Yeah? Okay, so maybe let's just, to simplify notation, let me write, so write qx theta to be precisely this second derivative, yeah, for some I and j fixed but arbitrary within the indices, right? Okay, so this is the log of x, that's just lowercase x, theta, yeah. Okay, so then, so let's bound the first term. We can bound the first term simply, so the first term is up there. And so this is important now, and is that, you know, remember this guy, the, you know, this intermediate value for the jth component of the gradient lives in this capital K, right? So we can bound really the absolute value of that guy by the sup over capital K, right? Of the q, so in this case 1 over n, sum from k equal 1 to n of q x k, now theta, minus the expectation, right? And sorry, of that, so of the q. Theta. Okay, so now this looks very familiar, right? So we should do, because what we basically want to use here is this uniform law of large numbers now, yeah? Because we are now under a compact, right? This ball, this closed ball, and so really what we need to check is the conditions of this uniform law of large numbers, and so that's simple, because we say, well, since q is continuous, right, on this U, or this open set, and this is by, well, for all x, by, I think it was B, no, it must have been B1, so by B1, I think, together with B3, which was guaranteeing this expectation of the supremum, okay, then we can use precisely this uniform law of large numbers to conclude that the right-hand side above, so the supremum, so all of that guy, goes to 0 in PR probability. Okay. So then, I mean, of course, we want, by the way, so up here on the right, so of course we want these two guys to go to 0 in probability, right? Because then we'll be left with this negative Fisher information matrix, which is exactly what we wanted. If you remember the informal discussion that we had here, that's what we wanted. So I'm trying to show that, the first two terms are go to 0 in probability. Okay. So now let's now show the same for the second term. So let's start again by bounding it by something. So the second term is this difference of expectations. Okay, so then let's bound it as follows. Okay, so this guy, let's bound it simply by the absolute value. Q, so let's just rewrite it essentially. And so now what we're going to want to do here is that, well, these two guys are very similar. I remind you that this guy is random and will induce randomness in the first term, but actually this guy will convert to theta naught. Okay, I will come back to that in a second. It will convert to theta naught in probability, and so if we had continuity in these functions, then we could apply the continuous mapping theorem to say that precisely the difference will go to 0. Right? So that's the idea of what comes. So let's then say that that this function, that is, so it integrates out the randomness through x, but then we have a function in theta, then this guy is continuous. Yeah. Why is that? So on this open set for all x here, why is that? Well, by A1 plus B1, which is the differentiability, but we need more than differentiability so that we can transfer it to the expectation. And this is, something that is guaranteed from the discussions that we've had already. So we need this B3. And furthermore, as I said, this guy is going to convert in probability to theta naught. Yeah? That should be clear. So, I mean, this is a very simple calculation. What do we need to show? Well, we need to show that precisely the, this quantity, when taking the difference, this can be simply written as the probability of Tj of the theta n hat minus theta naught. And then, of course, this is now bounded by the probability of precisely this. Yeah? And this is, this will go to 0 by consistency. Okay. Okay, so that's just, the consistency transfers to this because, of course, this is just an intermediate value between the theta naught and something that is converting to theta naught. Yeah? Okay, so we can apply, as I was saying, the continuous mapping theorem. By the continuous mapping theorem, we get precisely that this second term converges in probability and the PR to 0. Yeah? And so this AN hat, what we've shown is that it converges precisely to what we wanted, which is this minus Fisher information matrix at the true value. Yeah? Okay, that's great. So now what are we left with? Well, we need to, sort of use this relationship to sort of say something about these guys. And so then what we're going to need is to invert this AN, right? But this follows, the fact that we can invert it follows from what we just showed, because in particular, since this guy is invertible, or non-singular or invertible, doesn't matter. So will be this guy. Yeah. Otherwise, there would be a contradiction. Yeah? If it were not invertible and was still converting in probability to that, right? Okay. So, and this is, of course, always in sets of high probability. Yeah? So in sets of probability going to 1. As n goes to infinity, and that's fine. So remember, we're still working under these ENs from before, but you can work on the intersection of the two, and because they're both going to 1, or their probabilities are going to 1, then the intersection is also going to 1. Yeah. Okay. So as I was saying, then so what we get is that we can. So we can use this, and we have here that guy. Yeah. Okay, that's good. Maybe I forgot a square root then. Okay. Yeah, good. Now, so this guy, we know how to deal with it, because we know that we know in fact this converges to this inverse of the Fisher information matrix. And so really what we are left with is analyzing that other guy, which actually, as I said earlier, is not difficult. So note, then let's rewrite it as follows. So this guy is the square root of the sample mean of these quantities. So this is going to be the log of f x k at theta naught, but with a gradient, sorry. But we wish to subtract the mean or the expectation of this guy. Okay. And I have reminded you that this is 0 by observation 2. Yeah. Okay, so then if this is 0, then we're sorted, because then this converges in distribution to a normal distribution with 0 mean, and the covariance matrix of this guy, right? And so this is, of course, by the, well, maybe let's say 1, by the central limit theorem, yeah? By CLT. And now this covariance here, if you go back to your notes from a few lectures ago, then we know that this guy is exactly the Fisher information matrix, and then we just need to use Slutsky's lemma. By Slutsky lemma, we get exactly the conclusion here. Okay. Okay, so this shows the theorem. So this is the asymptotic normality of Emily. So let's now move on to making a few remarks about the theorem. Remarks. Okay, so the first one is that, so let's think about what we can drop and what we cannot drop about the assumptions. So we can drop the twice differentiability, okay? Twice differentiability, and substitute it by we can relax. Okay, so let's say relax, yeah, rather than drop. So relax. Differentiability to what is called weak derivatives. So maybe if you're doing some analysis course with distribution theory, then you'll see what a weak differential is, weak derivative, differentiability. And this is just one, yeah? So it's just one derivative, and actually a weak derivative, which is weaker, as you can expect, than a classical or a continuous differential derivative, yeah? Okay, so then we can, as I'm saying, we can have just simply weak differentiability of this guy, okay? And then, okay, and this is of course with more complex proofs. Excuse me, this has, okay. So with more complex proofs, but you'll be thinking, okay, so why is this of interest? Well, it is of interest because, of course, I mean, you know, dropping the differentiability will mean that we can consider much more general models, right? And so it may sound like, you know, one differential is not very much, but actually this will allow for models which are quite reasonable, such as the Laplace distributions. Yeah? Okay, which has, you know, this non-differentiability at the origin. Yeah? Okay, so for this, I mean, one needs to use what is called LeCam theory. It's certainly not part of the course, and this you can find in Art van der Vaart's book, 98, asymptotic statistics. So that should be in the schedules, that as a bibliography. Okay. Second remark. So we cannot drop this differentiability. Okay. So we cannot drop differentiability itself. Yeah? So you'll see this in the example sheet. Well, you must have seen this, or maybe it's in the next one. So example sheet. The example sheet, you see the following example, which is, you know, consider X to be a uniform distribution, and this is going to be on zero theta, where theta, you know, belongs to parameter space, which is going to be, I guess, contained or even equal to R plus. Okay. So of course, you know, fx theta is non-differentiable because it is equal to this. Yeah. Okay, so non-differentiable. And you'll see that there is no that the MLE will not be normally distributed, and this, by the way, has to do with the support depending on the parameter. Okay, so when the support depends on the parameter of interest or a known parameter, it's, you know, generally you know, the normality, asymptotic normality of the MLE will fail. Basically. Okay. So another thing that we cannot drop, that the theta naught belongs to the interior. Yeah? So if you're in the boundary, so in other words, if you're in the boundary, then you will not have asymptotic normality of the MLE in general. Okay, so this you'll see again the example sheet through the following example, which is one in which we have a normal distribution with the known variance, and the mean is going to be, say, you could take a different set. Important thing is that it's closed on one side, and so you'll get so asymptotic normality of MLE only on 0 infinity. So on 0, it will fail. Basically, that's what you have to show in the example sheet. Yeah. Okay, and let me now make a last remark. So 4, and this has to do with not so much with assumptions, whether we can drop them or not, but really with the statement. Okay, so in the statement we said that that we have this consistency first of all with a given rate of convergence, which is this square root of n, and then once we know the rate of convergence, then we're interested in the constant, so to say, which is in this case the variance, and then once we know the constant, once we sort of have a constant, then we can even think about the distributional properties, and so we get normality, and so this is very strong, the whole thing. But this constant, so this variance, we said that this is going to be optimal, right? So that we have this asymptotic efficiency. But actually, this optimality is not for all estimators, it's for some estimators, which are the desirable estimators. Okay, so let's talk a bit about this. So this Fisher information or Fisher inverse of Fisher information matrix is a lower bound only for so-called regular estimators. Okay. Well, sorry, let's say for the variance. Yeah. The variance of regular estimators. Okay, so, and this is again based on LeCam theory, which in this case will give a rigorous theory of this asymptotic efficiency. Efficiency through precisely extending or talking about asymptotic Cramer-Rao load bound. Yeah. Cramer-Rao. Yeah. Okay, so you will see in some example sheet later on, I think it's the third one. So we'll go back to this example. So now let me talk about it in the context of, in this context of this Cramer-Rao load bound, but we will go back to it in a different context, in which we will sort of talk about these desirable estimators, yeah? And why, the following estimator, even though it may do better than the MLE, is not really better in a sense that it's useful for statistical learning. Okay. So this is what is called, by the way, Hodge's estimator. Hodge's estimator. Okay, so let me define it. So how do we write it? So we have. So we can even consider. So let me just say. So let this theta n be an MLE for a model such that 0 is in the interior, okay, and this could be just any other value. Yeah? 0 as in that the interior is non-empty, but we can arbitrarily choose 0, so you could construct the Hodge estimator in a different point of the interior, but we do so for 0 because you can always sort of displace this space if you're in a Euclidean space or whatever, right? Okay, so then this and that, this and satisfying the assumptions of the last theorem, which is A1, A2, and B2. Sorry, B, just in general, B. Okay, so we define now theta tilde n to be, so this is Hodge's estimator, so this is going to be the MLE if this guy is larger than n to the -1/4. Okay, so if it is large enough, and then 0 otherwise. And this has to do, so this 0 has to do with this, with the 0 belonging to the interior. So, okay, as in you could define it to be a different value if you were, yeah, okay, so this that I was talking about. Okay, so let's now see the behavior of this estimator and the different parameters. So let's assume first of all that we have theta distinct from 0. Then what can we say about the following probability? So the probability, okay, so maybe PR I called it. So let me just write PR for P theta n. Okay, so the probability of this guy being distinct from this other guy is what? Well, it's the probability of being 0 for this other guy, and so this is just the probability of the MLE being less or equal than n to the -1/4, right? Simple. So we can add and subtract, we can add and subtract theta to this guy, and bound this guy above by, so if you use the reverse triangle inequality, then what you will get is that you can take this minus, so take this to the other side, and then take this guy to this side. Okay. And then, so theta is fixed, right? Because this is the generating parameter of the data. And so for n large enough, what we will get is that this guy is, if we like, that guy is going to be larger than or equal to this absolute value of theta, but now halves, say. Okay, so then what we get is that the probability, and this is for n large enough, okay? This is theta n minus theta being larger or equal than theta halves, say. And so because that value is fixed and we have consistency of the MLE as part of the assumptions of the B assumptions, then this of course has to go to 0. Yeah? This goes to 0 as n goes to infinity by consistency. Or this theta n hat. And so what does this mean? Well, this means that, again, these are some sets. So this set, so the set in which they are different is a set of probability approaching 0. And so we can work in the complement, and in the complement, we have that they are equal. And so by the reasoning that we used in the proof at the beginning of the proof with the ENs, with sets, then we have that square root of n of this guy minus theta converges in distribution to a normal distribution with this variance. Yeah. So this is just by the asymptotic normality of MLE. Okay. And this is, of course, under this PR. Yeah. Okay, so what about the case when theta is 0? Because so far, what we've seen is that the behavior is just the same at every other point. Okay, so, however, so let's now look at that case in which we have, so let me write now PR naught for P theta naught, sorry, not P theta naught, P0, okay, so that's a 0 now. So, however, under this guy, so as in if the true parameter is 0, then if we look at the probability of these two guys being equal, then what is this? Well, the 2 being equal is precisely, the first case, and so we have the probability of this guy being greater than n to the minus 1/2, to the minus 1/4, which is of course, the same as this. So that's a 0. That's the actual parameter of interest in this case. And so we can multiply by square root of n, right? Absolute value. So that's a 0. Okay. And we now have that. Okay, so now what we want to do. So remember, this guy is an MLE, and the MLE, by the assumptions, will have this asymptotic normality. And now we remember from a few lectures ago that we introduced what is called Prohorov's theorem. And so the first part, what it was telling us is that we have some sort of convergence in distribution, we have boundedness in probability. It doesn't really imply convergence in probability, but boundedness. And this boundedness is precisely going to tell us something about this quantity, right? So if you look back in the notes, so let's state this. So by Prohorov's, by the first half of Prohorov's, theorem, we get that this quantity, square root of n theta n hat, is going to be, as I was saying, bounded in probability. Yeah. And what this means is that for all epsilon, we can find a quantity large enough so that this whole probability is smaller than epsilon. Okay, and this means that for n large enough, we will be able to make this quantity as small as we like, essentially. Yeah. Okay, so then the right-hand side is arbitrarily small. Yeah. Of course, as the sample size grows. Okay. All right. And so then what we get is that the square root of this guy, what we get is that, the tilde, the Hodge's estimator is not really going to be the MLE, but rather it's just going to be 0, because that's what its value is out of this set. And so then this converges to 0 in probability, and this is like a normal distribution with 0 mean and 0 variance, yeah? And therefore, this is strictly smaller variance, yeah? Variance. Okay, so then this theta n, so the MLE, which has variance. I remind you, this I minus 1 at 0, which has to be positive. Yeah? So we spoke about this, that the Fisher information matrix is always positive. Yeah? Okay, so in regular models. Okay, so this is strictly smaller variance than this guy, but, you know, what is important about this is that the improvement is at a single point. Yeah? Point, which means not useful really, yeah? In statistics. Yeah? And so we'll come back to this. We'll return to this, because clearly we need some sort of I guess framework or definition to work with, because, you know, in this case we found something that works better than the MLE, but that is not really useful. So really what we want to say is that they're both sort of as useful or as useless, I guess. And this one is, I would argue, even less useful than the MLE, because, you know, of course, we're truncating a region to 0, and you know, for finite samples, this may be worse than the actual MLE. Yeah. Okay, so this we will return to this in the context of, so this is when we sort of cover minimax risk. Okay, so yeah, I hope you enjoyed the lecture, and I'll see you again in the next one.